Okay, so let's proceed with the chapter of direct current circuits. So before we entering our new subtopics, let's go through for some exercise that related to our current subtopic, which is the Kirchhoff law, which consists of Kirchhoff first law and Kirchhoff second law. So from the previous video, we are actually stopped at the question number 1. So let's go through for the question number 2. Okay, so this will be our second example. So our second example, we have a circuit diagram. Okay, so give me a moment. Let me just draw the circuit. Okay, so this is the first battery, and this is the first resistance. Okay, so this is the second battery, and finally this is the second resistor. Okay, so this both resistor is actually connected to each other. Okay, and the upper part, there will be the third resistor, which is located at here. Okay, so this is our circuit. So the first battery, we have the 3 volt for the potential difference, and for the second battery I have my 3 volt as well, and this is the first and the second current respectively. Okay, so this is I1 and this is I2. Okay, so let's see what else. So this is our 2 ohm resistance, and this is 6 ohm, and finally this is 4 ohm. So between this I1 and I2 will eventually produce I3, since the Kirchhoff first law tell us that the total current that entering the junction, so this is the junction, I consider this junction as A, and this junction, at the end of this junction, we consider as junction B. So this is junction A. So when I2 and I1 and I2 approaching the junction A will eventually produce I3 after combining to each other. Okay, so yeah, that is our circuits. Okay, so for the first question, the question is actually asking to find out what is the I1, I2, and I3. I2 and I3. Okay, so this is our first questions. Alright, so use what we have learned from the previous video. We learned about the concept of Kirchhoff first law and Kirchhoff second law. So based on the Kirchhoff first law, as I said just now, I1 and I2 approaching the same junction will produce the new current, which is I3 after leaving the junction. Okay, so based on Kirchhoff first law, so what I get is actually I3 is equal to I1 plus I2. So this is my first equation. Okay, so since we have 3 unknown, it means that we require the 3 equation. So where can I find the 3 equation? So after using the Kirchhoff first law, of course, we need to use the Kirchhoff second law. So the Kirchhoff second law tells us that the sum of the potential difference or the change in the electric potential in a closed loop, or I can say in a complete circuit, is actually equals to 0. So since I need two equations left, so it means that I need to find out the two loops, two complete circuits or the two closed loops. Okay, so what I found is actually equals is okay, so I how should I draw this? So consider my first loop is actually came from the lower parts. So this will be our lower parts. So this is actually the path for the current. So from the lower parts we move to the upper parts, which is the path after the current become I3. So pass through the upper parts and finally come down to the lower parts again. So this will be our first loop, which is okay. I think I just highlight or okay. I don't know whether you can see clearly. So this will be my first loop. So the green path indicates the first loop. Okay, so this green path is actually our first loop. So this is first. As for the second loop, okay, so for the second loop is actually comes from the upper parts. So the second loop, the second closed loop is actually came from this part and move from this second part, second floor to the third floor. So this black color path will be our second closed loop. So this will be our second. So of course the direction is actually in clockwise direction. Okay, so since we already have the two loops, two closed loops, it means that one loop is actually contribute to one equation, and since we have the two loops, so we got two equations. Okay, so for the first equation, so let's look for the first equation. So I prefer to begin with this first battery, which is 3 volts. Okay, so of course, based on the Kirchhoff's second law, Kirchhoff's second law, the sum of the potential difference, the change in electric potential, which is more accurate, in a closed loop is actually equals to 0. Okay, so for the first loop, start from the lower parts. Okay, so what we get is actually 3. So 3. So moving on to the upper parts. So we finally reach this third resistor. So this resistor has a potential difference, which is, so since potential difference V is actually equals to IR, so the potential difference across this 4 ohm resistor is actually 4I3. So this is actually the region for I3. So what we need to do is actually minus 4I3. So minus, same as from the previous part, which is the current flows from the higher region of electric potential to lower region of electric potential. So okay, so this is minus 4I3, And finally, return to the lower parts. So return to the lower parts, we finally reach the first resistor, or I can say the 2 ohm resistor. So this region is actually belongs to the first current, which is I1. So what we need to do is express in the potential difference in terms of this 2 ohms resistor. So if I prefer to write it as minus 2I1. So this is 2I1. Okay, so double check again whether there is something that we missed. Okay, so passing through the first resistor, 4 ohm resistor, and finally passes through the 2 ohm resistor. Okay, so I think that's all for the first equation. Okay, so it's equals to 0. Okay, so I prefer to derive it directly. So I prefer to express in terms of I1. Okay, so this 2I1 is equal to 3 minus 4I3. So this I1 is equals to 3 minus 4I3 divided by 2. So this is the first equation. This is the second equation, sorry. So this is the second equation. Okay, so we have done for the first loop. So what about the second loop? So the second loop, of course, based on the Kirchhoff's second law. So the tree, I prefer to start from the 3-volt battery. So moving on to the upper parts. So of course, same as the first loop, we passes through the 4 ohm resistor. So the 4 ohm resistor we need to minus 4I3. So I3 is the region of the third current. So moving back to the second floor, so what we have here is the 6 ohm resistor. So the 6 ohm resistor actually lies in the region of second current. So what we need to do is actually express in the form of electric potential. So the electric potential, we have the 6I2. So this is 6I2. So actually minus all of it. So what we get is actually the 0. Okay, so if I express in terms of I2, so this is 6I2 equals to 3 minus 4I3. So I2, what we get is actually 3 minus 4I3 minus 6 divided by 6. So this is the third equation. Okay, so we have all the equation that we need. Okay, so what we need to do is actually subs 2 and 3 into 1. Okay, so if I subs 2 and 3 into 1, so the I3 is equal to I1. So my I1 basically is 3 minus 4I3 divided by 2. So plus the 3 minus 4I3 divided by 6. Okay, so if I resolve it, so this is so if I multiply this one as 3 and this is 9, okay, 3 times 3 is equal to 9, so 4 times 3 is equals to 12. So this is 6 plus 3 minus 4I3 divided by 6. So this is 6I3 equals to 9 negative 12I3 plus 3 minus 4i3. So if I resolve it, my i3 basically will get okay, so let me see, 0.545 ampere. So this is the current for i3. Okay, so what about i2? Okay, so where's my i2 equation? So let's move on to I1 first. 3 minus 4, 0.545 divided by 2. So what I get for the first current is actually equals to 0.137 ampere. So as for I2, I2 is 3 minus 4, 0.545 divided by 6. So what I get is actually equals to 0.41 ampere. So that is how we find out all the three currents inside the circuits. Okay, so as for the question part B, so the question part B is actually asking for the potential difference across the point A and point B. So I consider this one as VAB. Okay, so potential difference across A and B. So actually we have three choices if I'm not mistaken. We actually have the three choice. The choice means the three paths for us to move from point A to point B. As for the first choice, so for the first choice is actually this path. So this is the first choice, and this is for the second choice, and finally this is for the third choice. So first choice is actually move in the clockwise direction, and the second choice is actually move from here to here, but in the opposite direction to the second current. So as for the third choice, we have the opposite direction to the direction of the first current. Okay, so what I choose is actually the first choice. Okay, so the first path is actually, okay, for me it's actually more easier since the electric components is consists only one resistor, which is the 4 ohm resistor. Okay, so let's begin. VAB is actually equals to, okay, so VAB is actually equals to the 4 times, okay, so this is negative since the potential difference across the 4 ohm resistor is negative. So for I3, so what will be my I3? So my I3 is actually 0.545 ampere. 545 ampere. Okay, so negative um, to be reminded, this one is actually I and this one is actually R. So V is actually equals to IR. Okay, so negative 4 times 0.545 is actually equals to negative 2.18 volt. So this is how we find out the electric potential across A and B. Okay, so I think we've done for the second question. Alright, so let's move on to the third questions. And this is the final example for the Kirchhoff law. Okay, so let's proceed. And this is the third example. So we have the diagram here. So this is the first resistance, and this is the point X, and this is the second resistance. And moving on, we have this point which is connected to the earth, and this is connected to the battery, and this is the battery. Okay, so this one should be shorter, and since this one is negative terminal and this is the positive terminal. Okay, so yeah, this is our circuit. And the first resistor we have the 300 ohm, and the second resistor we have the 500 ohm, and finally our battery is actually 40 volts. Okay, so our question is actually asking for the electric potential at point X. Find Vx. Okay, before that, what we need to do is actually find out what is actually the current that is flowing inside this circuit. So based on our prior knowledge, so our total resistor, which arranged in series, is actually 800 ohm, and we have the battery which is 40 volts. So E is equals to IR. So this 40 equals to I divided by 800, or you can write it as V is okay. So V is actually more accurate since the current is flowing inside the battery. So since the current is flowing inside the battery and the terminal potential difference across the battery is no longer electromotive force. Okay, so this one is 40 divided by 800. Okay, so what we get is actually equals to 0.05 ampere. So 0.05 ampere, we know that the 0.05 ampere is actually moving inside this circuits. Okay, so our question is find out what is actually the potential difference, electric potential difference across Vx. Okay, so we actually only have one path, which is this path. Okay, so we have only one path, so we can't choose this path as our path to point X. This is because along the path, so this conductor is actually connected to the center of the earth, and since the conductor is connected to the center of the earth and the current move until here, so the current will be disappeared. So hence that is why we consist of only one path. Okay, so I'll start from here, from this battery to point X. So 40 minus 300, 0.05. So this is our answer. So what I get is actually 25 volts. So that's it for the electric potential at point X. Alright, so I think we have done for the topics of the subtopics of the Kirchhoff law. Okay, so I think we will proceed now to our new subtopics. So okay, so let me find free space here. Okay, so we're going to discuss what is actually the potential divider. Potential divider. Okay, so assume I have a circuit. So I have my first resistor and I have my second resistor. So this will be my R1 and this will be my R2. Okay, so this is actually connected to our potential difference, not potential difference, our battery, and this is my V, of course. So this will be my I. Alright, so to be honest, the potential divider is actually used to find the potential difference across each resistor. So so um so let me see what is okay. So the potential divider, as I said, is used to find out the individual potential difference which across the uh, both resistor. Let's say I wish to find out the potential difference across the resistor 1. So if in order to find out the potential difference across the first resistor, so what we need to use is actually the concept of potential divider. So we're going to see how can we derive the potential difference across the first resistor. And okay, so first of all, what we need to do is actually find out the total resistance. So our total resistance is actually combine the first resistor and the second resistor, since the both resistor is connected in series, and this is our total resistor. Okay, so since V is equals to IR, so I prefer to write it as RT. RT means the total resistor. So I, that which moving inside this circuit, so it's actually equals to V over RT. So this is V over R1 plus R2. So I can find out that my R1, my I is actually equals to the V over R1 plus R2. Okay, so in order to find out what is the potential difference across the first resistor, so what we need to do is actually use the formula of Ohm's law. So Ohm's law states that V is actually equals to IR. So this R is actually no longer RT instead of R1. So I write this one as R1. So since my I is actually V over R1 plus R2, so I just substitute this formula. So what I get is actually V over R1 plus R2 times R1. So this is, I consider this one as V1, and this is V1 as well. Okay, so if I arrange it, R1 over R1 plus R2 times the total potential difference that produced by the battery. So what I get is actually the potential difference across the first resistor. And this actually also same goes to the potential difference across the second resistor. So what we need to write at the upper part is actually R2. So R2 over R1 plus R2 multiplied by the total potential difference. Okay, so that's it. That is what we call potential divider. Okay, so the potential divider is actually the output voltage, which is V1 and V2. So this V1 and V2 is actually the fraction from the input voltage. So our input voltage is basically equal to our V. So that's a concept. Okay, so I think we'll stop here now. So the time is actually quite longer. So From the next coming video, we're going to discuss about some examples that related to potential divider, and we will enter our new subtopics later. So I think we'll stop here now. If there's any question need to be asked, please comment below this video. So I'll see you next time. Thank you. Bye.